Alright, here we are with Unit 2, Assignment 6. This is the review for Unit 2 on derivatives. And so we're going to get going right away here. We're supposed to take the derivative of each function. It says do not simplify, so we're not going to worry about combining like terms and all that kind of good stuff. So this is a product rule, and so we're supposed to take y prime is going to equal the derivative of the first. That's going to be 28 x to the third. We're going to reduce the exponent by 1 plus 2, and that first part is done. The derivative of 3 would be 0, so we're taking the derivative of the first times the second, so that's going to be 9x to the sixth minus 2x to the fourth plus 8x, and then we're going to add the first part, so that's 7x to the fourth plus 2x plus 3 times the derivative of the second part. So I guess I do need to multiply and actually take the derivative here. So 6 times 9 is going to be 54 x to the fifth power. We're going to reduce the exponent by 1 minus 8x cubed plus 8, and we are done with that one. All right, the next one here. Before I do anything here on this one, I am going to rewrite this. This is really just I like my fractions written like this: 9/7 x to the third power. In the second piece here, I'm going to bring x squared up into the numerator, so this is going to be 3 times x to the negative 2 plus 7 pi. All right, so here goes y prime. Y prime is going to equal, this is just parts right here, so we're going to take the derivative of each part. Okay, so here we go. In the first part, we're going to bring that exponent down again, and we are going to, hang on here a second. I just got a text and I'm getting thrown off here. All right, let's try this again. So I'm going to multiply the exponent times the number in front. That's going to be 27/7 now. X to the second power, we're going to reduce the exponent. We're going to do the same thing in the next part. Negative 2 times 3 is negative 6x. Subtracting 1 from the exponent leaves negative 3. The derivative of 7 pi is 0 because 7 pi is a constant. All right, next, whoops, way too far here. Next one. Looks like we're going to do some quotient rule here on this one. So the quotient rule is similar to the product rule. Y prime is going to equal the derivative of the numerator, so that's going to be 3x squared times the denominator, 2x to the fourth plus 3x plus 1, and then we get minus, in this case, the numerator, which is x cubed plus 2, times the derivative of the denominator, that's 8x to the third plus 3, and then it's all over the denominator squared, so 2x to the fourth plus 3x plus 1, wrap that guy up in parentheses, put a squared there, and you're done. All right? Letter D is another product rule here. So think of these as two parts. 9x to the seventh is your first part, e to the x is your second part. Y prime is going to equal 7 times 9 is 63 x to the sixth power times the second one, e to the x, plus the first part, 9x to the seventh power, times the derivative of e to the x, which is just e to the x. Easy, easy, huh? Letter E, same thing, product rule. Y prime equals derivative of the first. That's going to be 2 times 3 is 6x plus 9. That's the derivative of the first. Times the second, 11x plus 13. Plus the first part, 3x squared plus 9x, times the derivative of the second part, which is just 11. That one's also done. More product rule in letter F here. I'm going to take g prime of a will equal the derivative of the numerator, that's 3a squared minus 4a, times the denominator, that's going to be e to the a plus 4a, minus the numerator, a cubed minus 2a squared, times the derivative of the denominator. Now, think about the denominator. The denominator is e to the a. So the derivative of e to the a is just e to the a. And then the derivative of 4a is plus 4. And then we need it all over the denominator. So e to the a plus 4a squared. All right, done with that one. The next one says not only to take the derivative dp dt, so take the derivative of p with respect to t, but then evaluate it when t is equal to 3. So the first thing I'm going to do is I'm going to take the derivative. So p prime would equal, again, this is going to be a quotient rule here. So we're going to do derivative of the numerator, that's 2t, times the denominator, e to the t. I guess I need a parenthesis there. Minus the numerator, t squared minus 1, times the derivative of e to the t, which is e to the t, all over e to the t squared. All right? So now I'm going to plug in 3. So p prime of 3. Here we go. Let's see what we get there. This is going to be 2 times 3 times e to the third minus, what do we got? 3 squared minus 1 e to the third all over e to the third squared. All right? Now, depending on what we're going to do with that, we could leave it, we can simplify it. I'm actually going to simplify this one. So let's see what we get. We get p prime of 3 is equal to, we've got 6e cubed for the first part, 6e cubed. In the second part, we've got 9 minus 1, which is 8, so that's going to be negative 8e cubed, all over e cubed squared is e to the 6th. In the numerator, I can factor out an e cubed, so I'm going to go ahead and do that. In fact, yeah, I'm not going to be able to cancel anything else, so I'm just going to factor out an e cubed. That's going to leave me with 6. Oh, you know what? I just realized those two have the same exact exponent, so I can go ahead and actually subtract them. That's negative 2e cubed. That's a lot easier than over e to the 6th. And then now I can cancel off my e's, so p prime of 3 turns out to be negative 2 over e to the third power. That wasn't so bad, was it? Didn't it look? All right, next page. Use the definition of the derivative to find f prime of x if f of x equals 3x squared minus 2x. All right, you got to remember, definition of derivative says dy dx, okay, dy dx, delta y over delta x, which is the same thing as saying f prime of x. All right, so here's our formula. It's the limit as h approaches 0 of f of x plus h, there we go, minus f of x, all divided by h. All right, so we're gonna plug that in here. So I'm just gonna call this f prime of x. F prime of x. So I'm substituting x plus h in for x in the equation here. This is gonna be 3 times x plus h squared minus 2 times x plus h. So that's just the first part. That's only f of x plus h. Now I need to subtract f of x. So I need to subtract the original function, 3x squared minus 2x, and then I'm going to divide that whole thing by h. All right? So we've done enough of these at this point. F prime of x, I'm going to go ahead and just FOIL out x plus h. So this is going to be 3 times x squared plus 2xh plus h squared. All right? We'll go ahead and distribute the negative. That's going to be minus 2x minus 2h minus 3x squared plus 2x in the numerator, all over h still. Oh, you know what? What did I forget here? I forgot the limit. The limit as h goes to 0. F prime of x equals the limit. All right? The limit as h goes to 0 equals the limit as h goes to 0 equals the limit as h goes to 0. I forget those all the time for some reason. All right, so I'm going to distribute the 3. This is 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 3x squared plus 2x and all over h. Okay, let's do some canceling here. All right, 3x squared in the front, negative 3x squared in the back. Negative 2x in the middle, negative or positive 2x in the back, which leaves me the limit as h goes to 0 of, now you can see in the numerator, all I have left is 6xh, 3h squared, and negative 2h. I can factor an h out of all of those guys, so I'm going to do that as I simplify here. So I'd have 6x left inside, plus 3h, minus 2, all divided by h. So hopefully that made sense, because the whole idea here is to cancel these h's out. Once I cancel the h's out, I no longer have a situation where I'm going to end up with 0 in the denominator. So now I can plug in h for 0. This is 6x plus 3 times 0 minus 2, which is going to equal 6x minus 2. Now I want to go back to the original function for a minute. If you remember, your original function was f of x equals 3x squared minus 2x. Now here's the thing, you guys. We've already talked about how to take the f prime of x. All right, we've done this over and over and over. So even before I got done with this definition of the derivative, even before I got to this point of 6x minus 2, I should have already known that if I take the derivative of this function, I do 2 times 3, which is 6. I reduce the exponent by 1. I take the derivative of negative 2x, which is negative 2, and boom. These two better be equal to each other every single time. Cool, huh? All right, next one. Sketch the graph of f prime of x. All right, so it doesn't say that the left one is f of x, so that would have been some helpful information. And, oh, you know what? Nope, no, now I see what's going on. This is an f of x graph, and this is an f of x graph, and so we're supposed to sketch f prime on the same grid, okay? So I'm going to do that. We're going to go to orange here. So the first thing I'm going to do is I'm going to sketch, if this is f of x, then f prime of x has to be 0 here at the max, here at the min, and again here at the max. All right? Now, a couple of little notifications here. On this left side, okay, f of x, or f, is increasing. Therefore, f prime of x is greater than 0, right? Which means that my derivative has to be above the x-axis for this entire interval up to whatever that is, negative 1.5. In this middle section here, all right, so I'm going to do some highlighting, because I'm going to highlight, here's what I'm going to do, I'm going to highlight all the areas where I'm increasing. So I'm increasing here, and I'm increasing here, and therefore my derivative should be positive on those intervals. So check it out. From 1 to a little over 2, we'll just call it 2.5. I know that my derivative's got to be positive. Or my derivative's got to be positive, because that yellow section is increasing. And then these other parts that I didn't highlight right here, f is decreasing, therefore f prime is less than 0. So once I get over here to 2.5, I'm just going to let my derivative drop. And this middle section from -1 to +1, my derivative is negative because my graph is decreasing in there. All right? That's really all it takes here, ladies and gentlemen. Let me grab a different color again here. So on the next graph, I've got a minimum at, I don't know, wherever that is. Looks like it's going to end up right about here at -2.5, somewhere around there. I've got a maximum just a little past -1. I've got a 0 at 0, and I've got a max almost at 1 here. All right, so again, this is f of x up here. f is decreasing, which means f prime is less than 0, negative. So I know, let me do this. Let me highlight the sections again. I'm going to highlight just like I did before. Highlight in yellow, increasing here, decreasing everywhere else. So if I'm increasing, my derivative should be positive. If I'm decreasing, my derivative should be negative. So I know that somewhere in here, my derivative is negative, and in here, in this yellow section, derivative's got to be positive. In this next section, my derivative's got to be negative because f is decreasing. But guess what? My derivative, oh no, my function f is now increasing, which means my derivative's got to be positive, and then it goes back to decreasing, which means my derivative has to be negative. Alright? Alright, the next part says, explain how a function cannot be differentiable at a point. Okay? So there's a couple of things you want to remember about differentiability. Differentiability implies continuous or continuity. Alright? Therefore, if we take the contrapositive of that, not continuous implies not differentiable. Alright? So a function cannot be differentiable if it's not continuous. So that's number one, not continuous. If I'm not continuous, I can't be differentiable. Alright? Letter B. Maybe we have some sharp turns or cusps. Sharp turns. Sharp turs. No, that would be the word turns. I think you guys got it though. Sharp turns or cusps. Can't even say that word properly. Sharp turns or cusps. Okay, so that would be something like this. You know, like I'm just going to do a basic absolute value function. All right, because this is easy to explain. If you look at this function, there's definitely a sharp turn there, but why is it not differentiable? It's not differentiable because the limit of f prime on the left, and I'm just going to say, let's just say the slope on the left is -1, the slope on the right is +1. So f prime over here is equal to -1, and f prime over here is equal to +1. And if the derivatives are not the same, as x approaches this value right here, I'll just call this a. So as x approaches a, the derivative on either side is not the same. So when we say how a function cannot be differentiable at a sharp turn or cusps, we say that the limit as x goes to a from the negative side of f prime of x, not f of x, but f prime of x, does not equal the limit as x goes to a from the positive side of f prime of x. In other words, the slope on the left does not equal the slope on the right. And the last one that we rarely see, but you know we do see it pop up once in a while, is a vertical tangent line. Vertical tangent line. And a quick example of that would be a square root function that comes into the origin like this. That square root function has a vertical tangent line right here at x equals 0. Okay, so those are the three ways that a function cannot be differentiable. Let's go on to the next one. Moseying right along here. Got a lot of pages to cover. All right, so it says for the graph at the right, where does it appear to be continuous but not differentiable? Now, continuous means you don't pick up your pencil at all. So if I start at the left side and I follow the graph over here, I have to pick up my pencil, jump down here, and then jump back on the graph and come around here. And then I've got to pick up my pencil, jump over here. Now I get to a sharp turn or cusp. So there's actually, looks to me like there's two places here, because I've got another sharp turn or cusp. If I keep going, I follow it down, I've got another one down at the bottom here. So at x equals 2 and x equals 4, right? And we just gave this reason. This is a sharp turn. What does that mean? It means the limit as x approaches 2 from the negative side of f of x, excuse me, of f prime of x, does not equal the limit as x approaches 2 from the positive side of f prime of x. Now I could say the same thing about 4 from the negative side and 4 from the positive side, but hopefully that makes sense. Letter B says, where does it appear to be neither continuous nor differentiable? So now we're looking for holes or jump discontinuities, and so the first hole that I see is at x equals -4, x equals -4. I also see another one at x equals -1. So these two, again, we go back to what we just saw on the previous page. If I am not continuous, right, not continuous, that implies not differentiable. Okay, how do I know I'm not continuous? Well, let's just look at x equals -4. The limit as x approaches -4 of f of x does not equal the value of f of 4. So therefore I'm not continuous, and not continuous means not differentiable. All right, find the equation of the tangent line. Oh boy, tangent line. Love equations of tangent lines. I need a point, and I need a slope. All right, let's read on. Tangent line of the curve y equals 3x cubed over x minus 1 at the point where x equals 2. All right, they already gave me half the point. I love that. So next thing I need to do is plug in 2. All right, so here we go. Y of 2 is going to equal, we've got 3 times 2 cubed over 2 minus 1. The tops, or the denominator is just going to be 1, so all I got to do is worry about the numerator. 2 cubed is 8, 8 times 3 is 24. So at the point 2 comma 24, I need a slope. All right, the slope requires a derivative. So now we need to do y prime. Y prime is going to equal, this is a quotient rule here, so we're going to do the derivative of the top. That's going to be 3 times 3 is 9x squared times the bottom, x minus 1, minus the top, 3x cubed, times the derivative of the bottom, which is just 1. So I don't really need that in there, but I'll put it in there for you. All over the bottom squared, x minus 1 squared. Now, I'm not even going to mess with simplifying that because I know I have to plug in 2. So y prime of 2 is going to equal 9 times 2 squared times 2 minus 1 minus 3 times 2 cubed. I'm not going to worry about the times 1 there. That's kind of ridiculous. And then in the denominator, I have 2 minus 1 squared. Well, again, you can see that the denominator is going to turn out to be 1, so I don't care about that. I'm just going to worry about the numerator. Got to pay a little more attention up here. So 2 squared is 4, and 4 times 9 is 36. The parentheses is 1, so I end up with 36 minus 2 cubed is 8. 8 times 3 is 24, and so I end up with 12. 12 is the slope at x equals 2. If we were to graph this function, we could show that we have a slope of 12 at x equals 2. Okay? So now we need the equation of the line. We need y minus y1. So here's my y1 and my x1 right over here. Got those right up front. Y minus 24 equals the slope 12 times x minus x1. I'm done. I'm leaving it there. All right. Number 8 says graph f of x equals the absolute value of x minus 5. All right. So we're going to do this quick and simple. X minus 5 means I'm going to shift to the right 5. 1, 2, 3, 4, 5. This graph has a slope of 1 to 1. So up 1 over 1 on the right, and then a negative 1 on the left. Close enough, right? All right. Letter B says write it as a piecewise function. Well, if I'm going to do this as a piecewise function, that means I'm going to do f of x, and I'm going to write the left half of the graph as one function, so that's going to be a linear function. So f of x equals, now imagine this line, it's got a slope of -1, which means it touches the y-axis up here at positive 5. So my first graph would be literally the left side of this is y equals negative x plus 5. All right, so all I need, I've got my y equals, all I need is the negative x plus 5. The other side would continue to come down and hit the y-axis at negative 5. So the right side would just be y equals x minus 5. Cool how that works, huh? So there's my second part of my function. All right, so there's my piecewise function right there. Now I do need some restrictions since it's a piecewise. This first graph only gets to go until x is equal to 5. So I need to say x less than or equal to 5. And because I included 5 on the first graph, I need to exclude it on the second graph. So I'm going to say x is greater than 5 on the second graph. You can't use the equals in both parts. All right? Next part says, take the derivative of the piecewise function. So f prime of x. Now, if you've listened all the way along, you should already know what the derivative is because we've talked about this derivative over and over. The derivative of my first function is negative 1 when x is less than or equal to 5. The derivative of my second function is positive 1 when x is greater than 5. So there's my derivative function, and explains why it is not differentiable at x equals 5. Well, we've talked about this. We did it a couple of pages back. I know that the limit as x approaches positive 5 from the negative side is equal to negative 1, and the limit as x approaches 5 from the positive side of f of x, f prime of x. I forgot my f prime on the other one. Let me go back over here and fix that. The limit as x approaches 5 from the negative side of f prime of x, okay, equals negative 1. And this one, from approaching from the right side or the positive side, equals positive 1. That's one way you could write that, okay? That's basically the same thing as saying, look, the limit as x approaches 5 from the negative side of f prime of x is not equal to the limit as x approaches 5 from the positive side of f prime of x. Therefore, I am not differentiable. Right. Page 3 done. Wow, we're just rolling right along here, aren't we? Okay. Let's see. Let's pick a different color here. Getting bored of orange. All right. The graph of f prime is shown to the right. On what intervals is f of x increasing and decreasing? Now, here's the thing again. If f is increasing, that means my derivative is positive. So because my derivative is positive here and my derivative is positive here, that means f must be increasing on those intervals. All right? So f prime greater than 0 implies f increasing. F prime less than 0 implies f decreasing. That means that I am increasing on the intervals from, what is this, 1, 2, 3, 4, from negative infinity to negative 4, and on the interval from negative 1 to infinity, because f prime is greater than 0, which implies that f of x is increasing. All right? So that means that I am decreasing on the interval from negative 4 to negative 1 because f prime is less than 0, which implies that f of x is decreasing. Okay? All right. And then it asks me to do some other stuff. So I'm actually going to erase my little, these guys here, because it says if f of negative 4, so now we're talking about f, not the derivative. Remember, this graph over here is the derivative. If f of negative 4 is equal to positive 4, so I'm going to plot that right away. If f of negative 4 is equal to positive 4, so check it out. 1, 2, 3, 4. Look at that. That's where my derivative is equal to 0. 1, 2, 3, 4. So if my derivative is equal to 0 right there, that means that point either has to be a max or a min. We'll talk about that in a second. F of negative 1 equals negative 3. 1, 2, 3. Notice right there, my derivative again is 0. So that's got to be a max or a min. So we said earlier that on the left side, f is increasing. We said that down here, f is decreasing. And over here, f is increasing. So if f goes from increasing to decreasing, that means that this guy up top here must be a max. So f goes from increasing to decreasing. I've got a max. All right. And then at the bottom point down here at negative 1, negative 3, my derivative goes from negative to positive, which means f goes from decreasing to increasing. So this guy's going to roll down here. I'm going to end up with a min right there, and I'm going to go to increasing as that graph heads off to infinity. And I should probably have an arrow over here too. All right? So f of x would look something like that. Not perfect, but something. Find the equation of the tangent line and the normal line, so the perpendicular line. Find the equation of the tangent line. Okay, so let's work with that one first. We need a tangent line of f of x when x equals negative 1. All right, so let's mark x equals negative 1. So x equals negative 1 is right here, but that's not f of x, that's f prime of x. But you got to look closely here because this problem actually just got way easier than you think it is. In order to do the equation of a tangent line, I need a point from f of x, and I need a slope at that point. Now, a derivative is a slope. I need f prime of negative 1. Well, guess what? We just plotted f prime of negative 1. F prime of negative 1 is 0, which means I got a 0 slope here. Okay? F prime of negative 1 is 0, so that's the slope at negative 1. We have very little work to do here, guys. All the information is staring us right in the face. So I've got my slope. I need my point when x is equal to negative 1. Well, let's go back up and look at C, or excuse me, B. Check it out. It gave me a point right there, negative 1, negative 3. So there's my point. I've got my slope, and I just need to plug it in. Y minus negative 3 equals 0 times x minus negative 1. Well, the whole right side is just 0. This is y plus 3 equals 0. So I end up with y equals negative 3. All right? So now it says then a normal line, a perpendicular line to that tangent line. All right? So I'm just going to draw the tangent line. The tangent line is at y equals negative 3. I just want you to see what's going on here. So y equals negative 3 is my tangent line. Hey, that makes perfect sense, doesn't it? Why would the tangent line be negative 3? Because I'm at the bottom of that little min right there. And at the bottom of the min here, my tangent line should have a slope of 0. Isn't that cool how all that plays together? Now, take a look at perpendicular to that. All right? I'm going to draw perpendicular to that. Ooh, boy, there we go. Perpendicular to y equals 3 through the point, negative 1, negative 3 would be perpendicular is x equals negative 1. See how easy that was? Not so bad. You just got to be able to break it down piece at a time there. All right? All right. Evaluate. Oh, more derivatives. Oh, wait, it says evaluate the derivative at 3 comma 9 halves. All right, well, first thing we need, I guess, is a derivative. All right, so we need f prime of t. So f prime of t is going to equal. Now, you got a couple of different ways you can do this, but I'm just going to do it by the quotient rule here. There's other ways that you could possibly do this, but the derivative of the top is 0 times the bottom, t minus 1, so that whole thing is going to be 0, minus the top, 9, times the derivative of the bottom, which is just 1, all over the bottom squared, t minus 1 squared. So f prime of t is simply going to equal negative 9 in the numerator and t minus 1 squared in the denominator. All right? So that's my derivative. Now, the 9 halves, I could care less about. It says evaluate the derivative at 3 comma 9 halves. I don't care about the 9 halves. All I care about is what's the value of t. T is equal to 3. So I need to find f prime of 3. So that's going to equal negative 9 divided by 3 minus 1 squared. So I'm going to end up with negative 9. 3 minus 1 is 2. 2 squared is 4. And hopefully we see a negative 9 first. Oh, look at that. Letter A. Of course, we're all getting A's today, aren't we? All right. Last page here. Okay, it says use the definition of the derivative. Okay. Now, it seems to me like we already did. Oh, we did do one of these, didn't we? Yep. You know what? Heck, I'll leave that one to you guys. All right. I'll just tell you this: when you get done, f prime of x should equal. Oh heck, we'll do it anyway. Why not do it, right? Okay, here we go. All right, so f prime of x. Okay, so we got the limit as h goes to 0. All right, one more time here. 2 times x plus h squared minus 3 times x plus h plus 1 minus f of x, 2x squared minus 3x plus 1 all over h. Now, I've multiplied out x plus h for you many times, so it's just x squared plus 2xh plus h squared. I'm going to go ahead and multiply it by 2. So this is the limit as h goes to 0 of 2x squared. We got 2xh times 2 plus 4xh plus h squared times 2, which would be 2h squared. Distribute the negative 3, that's minus 3x minus 3h. Bring down the plus 1. Distribute the negative, that's negative 2x squared plus 3x minus 1. See how quickly you can actually do this if you know just a little bit of mathematics in your head. So this is the limit as h goes to 0. Alright, before I do that, I'm going to do some canceling up top here, so let me get a different color here. 2x squareds are gone. Negative 3x, positive 3x gone, plus 1, minus 1, and I'm back to having h's in all the terms up top, so I'm going to factor out h. I have 4x plus 2h minus 3 left over. H is still on the bottom, but now I can cancel those, and once I cancel, I can plug in 0, so the 2h goes away, and I get 4x minus 3 as my derivative. Now, again, if you look at this original function, you should see that right away. If you bring the 2 down in front and multiply, that's going to be 4x. The derivative of negative 3x is negative 3. I knew that before I even started. Nifty, nifty. All right, the graph of g prime is shown. Tell where g of x would have maximums and minimums. So I know that g of x has max and mins where g prime is equal to 0. Okay, so g of x has max or mins when g prime of x is equal to 0. Right away I know that I've got either a max or a min here at negative what, 1, 2, 3, 4, negative 5, negative 1, and positive 2. I just have to figure out whether those are maxes or mins. All right? So my derivative, again, I'm going to go back to doing some highlighting here. When my derivative is positive, that means that f is increasing. You got it. So I know that f is increasing. F is increasing here. F is increasing here. That means f is decreasing here, and f is decreasing here. All right? So if I go from decreasing to increasing, think about that. Decreasing, decreasing, decreasing to increasing, 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 that is a min. Decreasing to increasing is a min. All right? And then I've got another decreasing to increasing over here at x equals 2. All right? So let's start with the mins. All right? So g of x has a min at x equals -5 and x equals +2 because f prime of x, oops, it's not f prime, g prime, sorry. Because g prime of x goes from negative to positive, which then implies that g of x goes from decreasing to increasing. So you have to mention that g prime goes from negative to positive before you can say that g of x goes from decreasing to increasing. All right? And then I've got a couple others here. We've got a couple of negative, or a couple other numbers where we have maxes or min. Actually, we only have one more right over here. X equals -1. G of x has a max at x equals -1 because g prime of x goes from positive to negative. So my derivative is above at the left side of -1 and below on the right side. So g prime goes from positive to negative, which implies that g of x goes from increasing to decreasing. All right? All right. Let's see what we got. Last one here. G is a continuous function on the interval from -3 to 10. Some of the values of g are given in the table. Is there a value of x on the interval such that g of x is equal to 4? All right. Well, let's just go through our chart. I go from -5 to -8. That doesn't imply that there might be a positive 4 in there. Then I go up to -1. I go up to 3. I still haven't made it up to 4 in there. Now, could I have made it up to 4 in there somewhere? Absolutely. But when I jump from 3 to 7, I know that this interval right here from 5 to 7, I know that there's got to be a g of x value equal to 4 in between 3 and 7, because this is going up from 3 to 7. Now, so I could use the interval from 5 to 7, okay? 5 to 7, I could use the interval. I could also say, look, you know what? On the interval from -3 to 7, there has to be a value. -3 to 7. Why? Because -3 is -5, and when x is equal to 7, f of 7 is equal to 7. So there's got to be a 4 in there somewhere too. I'm just pulling the smallest interval. So the answer here would be yes. Since, right, and this is a big deal, since g is continuous, and g of 5 equals 3, and g of 7 equals 7, then there is an interval from 5 to 7 such that g of x is equal to 4 by intermediate value theorem. Ta-da! We are done, ladies and gentlemen. Hope that helped.